Audio Jungle.
Welcome to AP Chemistry. Today we're going to take a look at what double replacement reactions are, what single replacement reactions are, how we're going to predict their products, and then we're going to look at some real-life examples to see if we predicted them correctly. So, part one, we're going to cover the two different types of reactions. And the first of those is a double replacement reaction. So, in a double replacement reaction, what we're going to do is we're going to put two chemical species into a beaker, and we're going to see, hopefully they will react. So it's called a reaction. So our first example that we're going to use, we're going to put some potassium iodide into this beaker. And we're going to notice that when we do that, because potassium iodide is soluble, it will dissociate into K+ ions and I-, which are positive potassium ions and negative iodide ions. And the reason that we know that this is going to separate is because we have a list of our solubility rules, which are going to become very important in AP Chemistry. And so probably the most important rule, if you want to know one of your solubility rules, this is the one you should know, is that anything that's in column 1 of your periodic table, which are your alkaline metals, those are going to be soluble. So because we have potassium in here, which is from column 1, we know for a fact that this is going to be soluble. So what we're going to be mixing with that potassium iodide is some lead nitrate. So lead nitrate looks like this. So it's represented by PbNO3 taken twice, and I apologize for the formatting of this. The program I'm using won't let me do the little 3 and the little 2, so sorry. But so it is 1 lead and 2 nitrates, and that's going to dissociate into a lead ion that has a charge of +2 and a nitrate ion that has a charge of -1. So now that we've examined our two species separately, and we've seen that they're both soluble, we know Ki was soluble because it was one of our column 1, and we know that lead nitrate is soluble because nitrate is one of our ions that are also always soluble, which is another rule you should know, is that nitrate and ions are always soluble. Now, what's interesting is we're going to look at what happens when they are combined. Okay, so let's watch. The lead nitrate is in the dropper and potassium iodide is in the beaker. And when we combine these two species, we can clearly see that a reaction has occurred because we can see a precipitate. This is one of the rules. A double replacement reaction has only occurred if we can see a visible change that is either a precipitate or a gas, which we will mention later. A solid. How can this be? How did we get a solid from two aqueous solutions? Let's rewind a little bit. So we started out with lead nitrate and potassium iodide, which we showed were both soluble. And when we have a double replacement reaction occur, what happens is that they switch places and they switch partners, so to speak. And so we end up with lead iodide and potassium nitrate. Now we know that column 1 and column 2 are always soluble and nitrate's always soluble, so that means that our potassium nitrate is double soluble, which really isn't a thing. All we need to know is that it's definitely not the solid, which means that our solid must be lead iodide. So if we look back at our solubility rules, which as you're going to see are very important to know, we do find that iodide is soluble with everything except for silver, lead, or mercury. So we can clearly state that a reaction has occurred because we have a precipitate, and that precipitate is our lead iodide. Okay, so we did say that there was one other way we can get a reaction to occur, and that's when a gas forms. So example we have this time is calcium carbonate, which are just marble chips, and that's being added into a solution of aqueous HCl, which is hydrochloric acid. So this is our first half of our equation written out. So we have calcium carbonate and hydrochloric acid. And what's going to happen when those ions switch partners, so to speak, is that we get H2CO3 and CaCl2. But what exactly does this mean? Because carbonic acid, which H2CO3 is carbonic acid, we don't see that by itself very often, and there's a reason for that. Let's take a look at what happens when we put the marble chips into the hydrochloric acid. Bubbles forming. So what are these bubbles? Well, to reiterate, our products of this reaction were H2CO3 and CaCl2. And H2CO3, also known as carbonic acid, has a special property. When carbonic acid is in water, it is really unstable. And what happens is it dissociates very rapidly into water and CO2 in the form of H2O as a liquid and CO2 as a gas. And so those bubbles that you see are carbon dioxide bubbles, which are used to carbonate your drinks and all sorts of things like that. So that is another way that we can have our double replacement reaction occur, is we don't necessarily have to have a precipitate, but we can also have a gas. And there are a few other gases, not just carbonic acid, but if we have sulfuric acid, that goes into sulfate and water. If we have nitric acid, that goes into nitrous oxide, nitrogen dioxide, and water. Or if we have ammonium hydroxide, that's going to go into ammonia gas and water. Okay, so far we've seen that double replacement reactions are successful, I guess you could call it, when you form a precipitate or one of the specific gases. But now we are adding to this list that they are successful, or they successfully react when they form pure liquid. And an example of this would be liquid water. And so a type of reaction that commonly produces liquid water is a neutralization reaction. And this happens when you mix a strong acid and a strong base, and that's going to produce water and a salt. So for example, we've got hydrochloric acid and sodium hydroxide. And when those switch places, you get hydrogen hydroxide, which is really just water, and table salt, which is aqueous. And so this is a successful reaction because you have produced water, which is a pure liquid. And again, that is called neutralization because no longer do you have something very acidic and something very basic, but you have a very neutral solution. So that is another way that you can have a successful double replacement reaction, is by producing that liquid water. Okay, so now we're going to take a look at our other type of reaction that we're going to focus on, which is the single replacement reaction. So the single replacement reaction, we're going to do a little illustration to illustrate what this is. So we're going to take a look at the Flintstones, and they're going to demonstrate for us what a single replacement reaction is. So let's say that Fred and Wilma are living very happily together, but then one day Betty comes into town, and she's this new girl, and Fred has a greater attraction to Betty because Betty is more attractive than Wilma. This causes quite the scandal, and in the end of their interaction, Fred and Betty end up together, and Wilma ends up alone. This is just like a single replacement reaction in that Fred and Wilma are the compound that is present, and Betty is the single species that's present. And what happens is Betty obviously has a greater reactivity than Wilma did, and so she's gonna knock Wilma out of her spot and replace her, hence the name single replacement. And so some terms I used there that were very important were reactivity. So we're going to make sure that we take a look at the reactivity series, because these single replacement reactions are only going to occur if the single species, which in this case is Betty, has a greater reactivity than our species that was already in the compound, which in this case was Wilma. So this is the reactivity series, and it's in order from most reactive to least reactive, and it goes through potassium, sodium, calcium, magnesium, aluminum, zinc, iron, tin, lead, copper, silver, gold, platinum. And later on in chemistry, you're going to look at what are called oxidation and reduction potentials, and that's sort of going to explain to you why this is organized the way that it is, because there's actually numerical values that you can put onto these metals that help us get this order, but you'll get to that later in the year. For now, just know that in order for a reaction to occur, the single metal has to be more reactive than the metal that's already in the compound. So let's take a look at one example that is not from the Flintstones. So the example that we're going to look at is actually one from a lab that you did if you had Mrs. Tyndall for honors chemistry. And so what you did was you put a copper wire into a solution of silver nitrate. And because copper is higher on the reactivity series than silver, the copper is going to replace the silver, and you are going to get silver as this hairy substance on the wire. And so you're going to have silver get kicked out and end up with copper nitrate, which is a bluish solution. And so that is an example of a single replacement reaction that does occur because you have one species that is higher up on the reactivity series than the other, and it replaces it. And that is the criteria that a single replacement reaction must meet in order to happen. Wow, I really feel like we've been through it all, and to think you haven't even begun AP Chemistry yet. So let's go over everything that we learned throughout this video. So we started looking at double replacement reactions, which, if you'll remember, are when two compounds mix. And for a double replacement reaction to occur, it must result in either a precipitate or a gas, otherwise no reaction has occurred. And so you're going to need to brush up on those solubility rules to know when a precipitate's going to form, and you have to memorize those gases to know when a gas is going to form. And after we looked at double replacement reactions, we looked at single replacement reactions, which are very similar, except instead of two compounds mixing, this time it's one compound mixing with a single metal. And in order for this to happen, the single lone metal must be more reactive than the metal in the compound based off the reactivity series. Otherwise, nothing's going to happen. So thank you guys for watching, and I hope that you've learned a lot throughout this video. And remember to check out the attached homework questions, because those are going to be great practice, and they're really going to give you a great head start. So I wish you guys the best of luck this year. Have fun in AP Chem.